What is pressure? Pressure is a force exerted over a specific area. We often think about pressure like water pressure, water pushing against the walls of a container, as shown in this figure. You can think of air pressure if you are diving deep underwater, or if you're in an airplane, you feel that pressure inside your inner ears. So anytime you have a force exerting over a specific area, there's a pressure involved. And the force is always perpendicular to the surface area. So if you have a force that is not perpendicular, then in order to calculate the pressure that that surface area is experiencing, you need to figure out the component that's perpendicular to the surface area. Now we're going to focus on gas and liquid pressure, and in those cases the force is going to be perpendicular. The units of pressure are known as the Pascal. 1 Pascal is equal to 1 Newton per meter squared. Now, pressure is also a scalar, not a vector. So even though force has a vector, has a direction associated with it, pressure does not. So you only need to worry about the magnitude of the force, and then just remember, if you want to know directions, that the force is perpendicular to that surface. Now, how exactly do we go about measuring pressure? Let's go through and imagine that we've got a little contraption that we're creating. So this is shown in the top figure here. This contraption is made out of a container with one end open, and in that open end is a piston. So a movable piece with a surface area of A, and that's connected to a spring inside of our little mechanism here. So when a force is exerted on that piston, on that little gray rectangular block, it can push the spring down. And we can use this to measure that pressure. So let's go through and take a look at how we would do this. So we know that the force exerted on a spring to be able to change and compress that spring by an amount, delta x, is equal to negative k delta x. And we've already talked about the force in a fluid being equal to pressure times area. So that means the net force on this piston that we're looking at here is pressure times area minus k times delta x. And if this piston isn't moving, then that's equal to 0. Our net force is 0. So we can calculate pressure with this little mechanism by doing a little algebra, and we see that that pressure is going to be equal to the spring constant of the spring inside, a known factor if we're building this little mechanism, the change in position of that piston, which is something that we could measure if we created this little mechanism, divided by the surface area of the piston. Again, something we already know. It's a property of the piece itself. So with this little imaginary measuring device, the more the piston is compressed in, the higher the pressure that it's experiencing. Now let's imagine that we put a bunch of these inside of a liquid. You can imagine doing this inside of a gas as well. So we can use them to measure the amount of pressure at different points within this liquid. If we go through and look at how compressed that spring is, where the piston is on our little measuring device at different locations throughout this liquid, we can see where the pressure is higher or lower. The more compressed the spring is, the higher the pressure. Now let's take a look at the causes of pressure. To do that, we'll start with an imaginary scenario. Let's imagine we have 2 sealed jars of a small amount of mercury. There's no air or anything else inside of these jars. On the left is what these 2 jars look like when they're taken into space. On the far left, the one marked liquid, the mercury is kept at a regular temperature, so it's still a liquid. And that little ball of liquid mercury, since this is up in space, is just floating together in a little ball. So it's not touching any of the sides of the container. Since it's not touching, there's no force exerted on it. There is no pressure. Now let's imagine that we heated that jar up so that liquid mercury turned into gas. So now we've got gas molecules bouncing around. Those molecules are colliding with the wall and sometimes with each other, and exerting forces, small amounts of forces, but forces nonetheless. Since there are forces being exerted on it, there is pressure on the walls of that container. Now let's imagine we take these two containers back down to Earth. We'll keep one liquid and one gas. When they're on Earth, that liquid that was a ball in space is now experiencing gravity. So gravity is pulling it down, and that liquid exerts a force on the bottom and some of the sides of the container. So there's pressure. If we take a look at the gas one, there was pressure before, but if you go through and take a look at it, and we'll actually draw some lines across the middle so you can see a little bit better, both for the weightless environment gas container and the gravitational environment gas container. So we'll divide these containers in half, and if we count the molecules for the weightless environment gas container, we see 5 molecules on the top and 5 molecules on the bottom, meaning that the pressure is the same everywhere. Now when we go through and do this counting for the one that's on Earth, we only see 4 on top and now 6 on the bottom. So they've redistributed a little bit, not as obviously as the liquid container has, but there are slightly more particles on the bottom than there are at the top, which means that the pressure on the bottom is going to be a little bit higher than the pressure inside this container on the top. And we'll take a look at this in a little bit more detail in a future video. Now, to conclude, what are the differences between these 4 jars? From the titles, one of them is two of them are in a weightless environment, and 2 are in an environment that's experiencing gravity. So gravity is one difference between these. The other difference is the difference that causes one of them to be gas and one to be liquid. And I mentioned earlier that that was based on temperature. We would have to heat the liquid up in order to turn it into gas. So we've got 2 differences, gravity and temperature. And these lead to our 2 contributions to the pressure of a container of fluid. A gravitational contribution arises from gravity pulling down on a fluid. And again, this is more obvious with liquid, but it does happen with gas as well. And that gravitational contribution will depend on the strength of that gravitational force. A thermal contribution is due to the collisions of that freely moving gas molecules or particles within the walls of the container. The thermal contribution depends, there's a bit of a typo there, depends on the absolute temperature of the gas. So that temperature of the gas will change the pressure of the container that's holding that particular fluid. And lastly, if we're talking about gases, the idea of vacuum often comes up. In physics, when we talk about a vacuum, we usually refer to that as being no air, molecules, anything exists inside of the container. Now, this isn't really realistic. In reality, no perfect vacuum exists, but we can get vacuums close enough to be able to approximate them such that the pressure inside that container that's under a vacuum is 0 atmospheres. But in reality, it's just very, very, very small.